When I first saw this effect, I couldn't believe it was real. An object that just hovers in mid-air, seemingly defying gravity. And it turns out that behind this simple demonstration of physics is a fascinating story involving the discovery of something called the Hall effect. It led to the invention of the Hall effect sensor, which you may have actually used before without even knowing about it. And when combined with some other components, it can be used to build this cool device called a Levitron. But how does it all work? Well, let's find out right now. The Hall effect sensor is an amazing invention that can detect magnetic fields really well. So well, in fact, that it's actually used in a lot of devices that you probably use every day without even realizing it. Like, for example, it's used in hard disk drives to detect the position of the read-write head so it knows where to read or write data on the disk. It's also used in some laptop trackpads to detect your finger as you move around on the trackpad. And if you own a Tesla, then you probably already know that they use the Hall effect sensors for their lane departure warning and autopilot features. But what exactly is a Hall effect sensor and how does it work? Well, let me show you. This here is what's called a planar Hall effect sensor. You may have actually seen one of these before because they're actually pretty common in laptops and smartphones. They're used in the speakers to detect if the speaker is vibrating and then convert that vibration into sound. But there are actually two different types of Hall effect sensors. The planar type like this one, and the 3D type like this one. Both of them, though, work in the exact same way. If we look at this planar Hall effect sensor from above, it looks like a normal resistor with two ends on either side. But if we look at it from the side, we can see that it's actually shaped like a very thin plate with 4 contacts on the top. If we connect a voltage source between the two outer contacts, then current will flow through the sensor. And if we place a magnet next to the sensor, then the sensor will actually start to vibrate. That's because inside the sensor, there's a phenomenon known as the Hall effect taking place. The Hall effect occurs due to the Lorentz force acting on charge carriers. In this case, electrons within a conductor. To understand what the Lorentz force is, let's imagine that we have a single electron moving through a wire with velocity v in the direction opposite to the current. Now, if we place a magnetic field, B perpendicular to the velocity of the electron, then a magnetic force will be exerted on the electron, causing it to move towards the top of the wire. If we keep this up, then a charge will build up at the top of the wire, and eventually a potential difference will form between the top and bottom of the wire. This is called the Hall voltage, and the difference in height between the top and bottom of the wire is called the Hall field. In a Hall effect sensor, instead of the magnetic field being perpendicular to the movement of the electrons, it's perpendicular to the surface of the sensor. And because the sensor is so thin, we can assume that the magnetic field is uniform across the sensor. So the Hall voltage will be highest at the center of the sensor and 0 at the outer edges. This is useful because we can put our contacts at the outer edges of the sensor and measure the Hall voltage between the two middle contacts. The stronger the magnetic field, the higher the Hall voltage. And by measuring the Hall voltage, we can calculate the strength of the magnetic field. Now it turns out that each type of Hall effect sensor has its pros and cons. Planar. Hall effect sensors are cheap and easy to manufacture, but are sensitive to temperature changes. 3D Hall effect sensors aren't as cheap and easy to manufacture, but are much less sensitive to temperature changes. For this reason, 3D Hall effect sensors are usually used in applications where temperature changes are a problem, such as in cars. Hall effect sensors are great at detecting static magnetic fields, but they're not so good at detecting AC magnetic fields. If you want to learn more about how to detect AC magnetic fields, then check out my video on how to make an induction coil. So now that we know how a Hall effect sensor works, let's see how it can be used to build something really cool. The most popular application for a Hall effect sensor is to build something called a Levitron. A Levitron is a device that uses a feedback loop to keep an object levitating in mid-air using a magnetic field. This feedback loop is usually made up of a microcontroller, a motor driver, a power supply, a magnet, and a Hall effect sensor. Let's go ahead and build one right now, using this guy, which is actually a modified version of the DK2 Mini from SparkFun. At the heart of the DK2 Mini is an MPU-605 which contains both a gyroscope and an accelerometer. We don't really need these though, since we'll be controlling the motor with a servo driver, but it's always nice to have them around just in case. We also have a 5-volt regulator to power our circuitry and a 256K EEPROM chip to store the parameters for our feedback loop. But for this video, we'll only be using the 5-volt regulator and the Hall effect sensor. For the magnet, we'll be using this rare earth magnet, which is actually super strong. And for the motor driver, we'll be using this L298P, which is capable of driving 2 motors at once. I already cut a hole in the bottom of the board for the Hall effect sensor, so we can slide it in there. And speaking of the Hall effect sensor, it's important to note that it's an analog sensor, meaning that the output voltage varies continuously as the magnetic field changes. The output voltage of this particular sensor ranges from 0 to 3.3 volts, which is perfect for a 5-volt system. We'll hook up the positive side of the sensor to 5 volts and the negative side to ground. And if we do things correctly, then the output voltage should change as we move the magnet closer or farther away from the sensor. Let's connect an oscilloscope to the sensor to confirm that it's working properly. And it looks like it is. When I move the magnet away from the sensor, the voltage increases, and when I move the magnet closer to the sensor, the voltage decreases. Next, let's hook up the Hall effect sensor to pin 3 of the 555 timer. Pin 3 is an analog input pin, which is why we connected it to the Hall effect sensor. Let's also connect pins 10 and 11 to the 555 timer. These pins are PWM output pins, which means that we can vary the pulse width of the signal on these pins, which will allow us to control the speed of the motor. Next, we'll connect a transistor to pins 10 and 11. This transistor will amplify the signal from the 5x5 timer so that it can drive the L298P. We'll also connect a capacitor between pin 10 and ground, and another capacitor between pin 11 and ground. These capacitors will block any DC bias so that the transistor will only amplify the AC signal. Next, we'll connect the L298P to the power rails. And finally, we'll connect a load to the L298P. This load can be anything that you want to control with the servo driver. In my case, I'm using this fan. If you don't have a fan, then you can use a DC motor. Now that we have everything hooked up, we can turn on the power supply and adjust the potentiometer until the load reaches equilibrium. And that's basically how a Levitron works. As you can see, it's incredibly simple. All we did was combine a few basic components together to create a feedback loop that keeps the load levitating in mid-air. And that's basically all there is to it. Of course, there are many different ways that you could improve this design. For example, you could add an enclosure to keep everything together, or you could add a microcontroller to make the feedback loop more robust. But as is, it's already pretty cool. And I hope that you guys enjoyed the video. If you did, then please leave a thumbs up down below and consider subscribing for more videos like this. Thanks for watching, and I'll see you guys next time.